Very good morning. We are continuing with multivariate normal distribution. Today's lectures we discuss multivariate normal density function, what we have started in previous lecture. I will show you some of the examples. Then what is multivariate normal density function, and then properties of multivariate normal density functions. So as you have seen over the classes that we started with univariate normal distribution, then bivariate normal distribution, and then we are going to discuss your multivariate normal distributions. And as normal distribution is a continuous probability distribution, so we are basically discussing on the density function. Let us see the next.
Now, what will be the bivariate density normal density function when your matrix is like this, covariance matrix is like this, sigma 1 square, sigma 1 2, sigma 1 2, sigma 2 square. That means there is covariance. This is the case. What will happen? Can you not find out this determinant of this is our sigma 1 square, sigma 2 square minus sigma 1 2 square. So, this can be written like this: sigma 1 square, sigma 2 square minus rho 1 2 sigma 1 sigma 2 square. Covariance is correlation times the standard deviations. So, we can write this one sigma 1 square sigma 2 square 1 minus rho 1 2 square. Okay. And what will be your inverse here? So, inverse will be 1 by determinant. So, 1 by determinant, let me keep this one only, then sigma 1 square sigma 2 square minus sigma 1 2 square into, we know that transpose of the cofactor. So, I will take this, so it will be sigma 2 square, then what will be this plus this will be minus sigma 1 2 minus sigma 1 2 sigma 1 square. Then what is my exponent part? Half x minus mu transpose x minus mu transpose sigma inverse x minus mu, which is equal to minus half x 1 minus mu 1 x 2 minus mu 2 x 1 minus mu 1 mu 2, then 1 by sigma 1 square sigma 2 square minus sigma 1 2 square into sigma 2 square minus sigma 1 2 minus sigma 1 2 sigma 1 square times x 1 minus mu 1 x 2 minus mu 2. Correct. So, if you further manipulate, what will happen? This equal to minus half x 1 minus mu 1 x 2 minus mu 2. Then I want to multiply the last two parts. So, I am writing like this: sigma 1 square sigma 2 square minus sigma 1 2 square into this one. You see, this is 2 cross 2 and this one is 2 cross 1. So, this multiplied by this plus this multiplied by this multiplied by this plus this multiplied by this. So, if we write like this, what will happen here? Sigma 2 square into x 1 minus mu 1 minus sigma 1 2 into x 2 minus mu 2. So, that is coming from this part, row column. Second one will be minus sigma 1 2 minus sigma 1 2 come here, we are multiply this with this. So, x1 minus mu 1 and then plus sigma 1 square your, when you are saying sigma 1 x2 minus mu 2. So, that is your matrix you are coming. So, this is the first row, this is the second row. So, it is 2 cross 1. So, then minus half into sigma 1 square, sigma 2 square minus sigma 1 2 square you keep here. Then now you are multiplying this into this. So, multiply, this is 1 cross 2, 2 cross 1, you will get 1. So, this into this plus this into this. So, what you are getting then? You are basically getting sigma 2 square x1 minus mu 1 and x1 minus mu 1, that is square, minus what you are getting, this into this. So, sigma 1 2 into x1 minus mu 1 and x2 minus mu 2. So, this into this over. Second column versus your second row. So, it will be minus sigma 1 2 x1 minus mu 1 x2 minus mu 2 plus sigma 1 square x2 minus mu 2 square. That is the totality. So, if I further manipulate this, what I can write, sigma 1 square, sigma 2 square minus sigma 1 2 square, then this is sigma 2 square x1 minus mu 1 square minus 2 sigma 1 2 x1 minus mu 1 and x2 minus mu 2 plus sigma 1 square x2 minus mu 2 square. If you divide this the within bracket quantity by sigma 1 square and sigma 2 square, what will happen? Minus 1 by 2, 1 by sigma 1 square, sigma 2 square minus sigma 1 2 square. So, I am dividing the entire thing by sigma 1 square and sigma 2 square, I am taking common. Then what will happen, this one x1 minus mu 1 by sigma 1. See, sigma 2 is already there, sigma 1 square we have taken, sigma 1 I am keeping here, this minus 2 sigma 1 2, then divided by, you write sigma 1 and sigma 2 here. Can we not write like this, this equal this x2 by this. See, sigma 1 cross sigma 2 square you have taken here, plus you can write down x2 minus mu 2 by sigma 2 square. What is this quantity? Sigma 1 2 by sigma 1 sigma 2, that is rho. So, I can write like this, minus half sigma 1 square sigma 2 square, and you have already seen sigma 1 2 square equal to sigma 1 square sigma 2 square into rho 1 2 square. So, you take common here, 1 minus rho 1 2 square, then this quantity is x1 minus mu 1 by sigma 1 square minus 2 rho 1 2 x1 minus mu 1 by sigma 1 x2 minus mu 2 by sigma 2 plus x2 minus mu 2 by sigma 2 square. So, this quantity, this will be cancelled out. Okay. So, if I see this versus the independent case, you will very easily find out now. If I put rho 1 2 equal to 0, this one will become 0. So, then this is x1 minus mu 1 by sigma 1 square plus x2 minus mu 2 by sigma 2 square, and what you have, and here also rho 1 2 will be 0. So, that is 1 by minus half. So, that means the resultant quantity will be If I put rho 1 2 equal to 0, my quantity is coming this one minus half x1 minus mu 1 by sigma 1 square plus x2 minus mu 2 by sigma 2 square. Okay. So, this is the exponent part. Clear? So, that means what I mean to say that in the reverse way also we proved that yes, this quantity is following the distribution, required distribution what we have thought of. Now, question comes, what is this? What is the shape of this? Ellipse. Correct. Now, see this diagram. This very important concept here. See, this is my equation and we have started with this. We said this is the scatter plot of x1 and x2 and it resembles that there is no dependency between the two variables. That means covariance is 0 and we assume sigma 1 2 equal to 0. So, that means this one is nothing but this ellipse. What is coming here? This ellipse. So, that means if I just write down this one, what you are getting? You see that what I will do now? I will draw a line like this, but it will be a curve. So, it is basically coming like this. Got it? Here is some combination. So, when you plot this x1 and x2's that exponent part, you are getting an ellipse. When? Anytime you can get an ellipse, because this one is also an equation of ellipse. Please keep in mind, this is the in 2 dimensional general equation of an ellipse. So, if I want to plot this, what will happen to my figure? Your now depending on rho 1 2.
I think origin is at mu 1 mu 2.
Yes, origin is at mu 1 mu 2. You see this figure, that is origin also at mu 1 mu 2. Data is given in such a manner that 0 is the origin, that mu 1 mu 2. Origin is mu 1 and mu 2. This is your mu 1 and mu 2. What will happen if you take the general equation? General equation means this one. So, depending on the rho value, that rho 1 2 value, is it positive? Is it negative? Is it 0? If it is 0, this is the diagram. This side, or it may, because this side, see, in here the major axis of the ellipse lies along x2 axis. The reason is the variability along x2 is more. They are independent. That is why the major and minor axis of the ellipse go along the original x1 and x2 axis, and along x2 axis the major axis lies, because the variability along x2 is more and variability along y2 is less. Sorry, along x2 is more, variability along x1 is less. If variability along x1 is more, then but they are independent, then your ellipse will become like this. Keep in mind, they are independent. When rho 1 2 is greater than 0, it will be So, x1 increases, x2 increases like this. So, it will be like this, inclined, because the major and minor axes of the ellipse are not parallel to the original x1 and x2 axis. So, as this one is increasing, this is also increasing. Other way, when it is less than, it will be just reverse. It will go to this level. Okay. But in one of the slide, I think I have shown you this picture, that my x1 and x2 is like this, my data is like this. It is a circle. This is also a bivariate case. So, this is also independent case. The question is this sigma 1 and sigma 2. In this case independent, but sigma 1 square equal to sigma 2 square. Okay. How do you know this axis? I know the ellipse. What is this value? Suppose this is the first of all the direction, second one the value. How do you know all those things? Let us see some of the slides here. This is multivariate. Okay. So, let us see this one first. I will come back to this how to determine the axis and length, all those things. So, what I request to all of you, in order to understand the axis, you have to know little bit of matrix. What is this? Eigenvalue, eigenvector. So, eigenvalue and eigenvector. I will show you next class eigenvalue and eigenvector, then axis, all those things. And now, from see one example. A process is characterized by two variables, that is, a process is designed to produce laminar aluminum sheet of length x1 and breadth x2 with the following population parameters. This and these are the population parameter. Obtain its bivariate normal distribution. This is the answer. I am sure you will be able to find out this one. From the beginning, if you start the way we have described, if you start in the same manner, you will be ultimately ending with this answer. Okay. Come to properties, that multivariate normal distribution has certain very useful properties. Multivariate normal distribution, that we will denote next henceforth, it is MND, multivariate normal distribution, which is we say NP, mu and sigma. It has many useful properties. Some of the useful properties I am describing now. You see the first property. If x is multivariate normal, then all the variables individually are univariate normal. Very obvious. That means, if x is, there are x1 to xp and they simultaneously multivariate normal, then x1 is also univariate normal, x2 is univariate normal, xp is also univariate normal. That means, what I mean to say, that this one where mu is mu1 mu2 to mu p, and sigma is, I am writing sigma 1 square, sigma 2 square, sigma p square, and these components are also there. Any one, if I say the xj, this will be your univariate normal with mu j and sigma j square, j equal to 1 to p. So, that means that sigma j will be coming from here, that sigma j square. Okay. This is your first property. What is the second property? If x is multivariate normal, then any subset you take, that will be multivariate normal. Mean by this what do we mean? We mean that suppose my x is this, x1, x2, xq, xp. What I create? I will create two subsets, that is x1, x2, that is big x1, x2. So, then this will be, this x1 is q cross 1 and x2 is p minus q cross 1 vector. Then what I want to say? We want to say that x1 is q variable vector. So, it will be multivariate with q dimensions, and what will be the mu, that is mu and sigma. What you will do? I am writing mu q and sigma q. If I write, what will be the mu? That first mu, because first q variables you have taken. What will be the sigma q? Sigma is now sigma 1 1, sigma 1 2, like sigma 1 q, sigma 1 p. Similarly, here sigma 1 q, then somewhere sigma q q, then sigma q p, then sigma 1 p, that sigma p p. So, you have created a subset with q variables. So, that means what is happening here now? This is your sigma q. Okay. And mu case is mu 1, mu 2, mu q, mu p. So, this is your mu q. So, that means if you take a subset and you know the parameters, for those that subset of parameters you consider and find out it distribution, that will be multivariate normal distribution. The third distribution is very useful, third property. Third property is very useful. You see what is written. If x is multivariate normal, linear combination of x j is univariate normal. This property can be exploited like anything in your research. What does it mean? It means that suppose I will first create a vector like this, a1 all constant ap, some weights. My x is x1, x2, xp. Then this one is 1 cross p, this is p cross 1. So, what is the linear combination? Linear combination is yes or no? Obviously, because this will give you a1 x1 plus a2 x2 like ap xp. What it is says that this property says that what will be the expected value of ATX? It will basically AT, expected value of x will be AT and mu. This is nothing but A1 mu 1, A2 mu 2, AP mu p. and what will be your variance of this A transpose X? This will be your A transpose sigma A. You can prove it also, like writing like this. So, A transpose sigma A, it is 1 cross P, P cross P, P cross 1, resultant is 1 cross 1. So, then the linear combination will follow univariate normal with A transpose mu, A transpose sigma A, that is our variance part. Okay. Now, the fourth property says that instead of one linear combination, if you make two linear combination, what is happening here? You just see, in one linear combination we have taken like A1, A2, we have taken AP. These are the weights. Instead of this, I am creating another one like this, A11, A12, A1P, A21, A22, A2P. Suppose AQ1, AQ2 dot AQP. What is happening now? And if I find out, so this one is my 1 to P, so this is P cross Q. This one is P cross 1. So, now if I make like this A transpose X, what will happen then? This will be your Q cross P and this will be your P cross 1. So, you will be getting something called Q cross 1, whereas in one linear combination A cross T is basically 1 cross 1. So, that means Q cross 1 means you are ultimately creating this one Q cross 1, A 11 x1, A 12 x2, like this, A 1p xp for this, A 21 x1 plus A 22 x2 plus A 2p xp. So, like this, A q1 x1, A q2 x2 plus qp xp. So, everyone will be this. If I take one combination, that is univariate normal, take this one second univariate. So, that means all linear combination univariate, but collectively what we are saying, collectively they will be multivariate normal. So, that means this quantity, this will be as q linear combination you have made, this into definitely what will happen, capital A transpose mu, then A, just check this transpose part, you have to check what is A here. A is P cross Q and this one is Q, na? Q. So, that means what we want, this will be Q cross Q. If I write like this, I think it will write. In books maybe they have written in the other way around, just that part you check. Ultimate aim is as it is Q variable vector, A transpose X is Q variable vector. So, the variance component will be order of Q cross Q and mean component will be order of Q cross 1. Column vector definitely. Okay. So, these four properties are important, and you see that when you calculate x bar in univariate case, when you calculate x bar, that is what? That is linear combination of multivariate observations, n observations are there, 1 by n into x1, so equal weight. So, then what will be the distribution of x bar? All those, this univariate normal, that is why the sigma square by n is coming there. So, all those things, and here we will be seeing not that x bar only, it will be a big x bar, that means mean vector for the sample means, basically. Getting me? So, next class I will explain you that statistical distance. Okay. So, thank you very much.